This DeBacco University video, hopefully I'll provide a good explanation of oxidation numbers so you have an understanding what these positive and negative numbers mean in this diagram by the end. All right, so oxidation numbers or oxidation states show how many electrons the atom they have gained or lost relative to their elemental state. This keeps track of electron ownership in reactions, and especially redox reactions. Remember, redox is short for reduction-oxidation. So we see examples of nitrogen-containing compounds in the various oxidation state of nitrogen. We could see it could be neutral, it could be -2, -3, +1, +2, +3, or even +5. And this has to do with nitrogen's oxidation number that you can see can be quite varied. So what do they represent? Well, they indicate the charge an atom would have if electrons were transferred completely. A positive number indicates the atom has lost electrons or has become oxidized. That's forming, for example, like a cation. Negative numbers, atom has gained electrons or has become reduced. Oxidation state is the hypothetical charge an atom would have if all those bonds to atoms of different elements were treated as ionic. It's another way to think about that. Some oxidative states where carbon isn't involved here. We can see some examples. We could see how H element oxidation state is provided, and they are typically positive or in the negative. And we can see when we have a +3 for iron, chlorine only has a -1, but there's 3 of them, so that will balance out, causing a neutral molecule there. What are some basic rules to assign oxidation numbers? Well, free elements or uncombined essentially would be 0. O2, Na, and Cl2 all have an oxidation number of 0. Monoatomic ions are equal to their charge. So sodium ion has a +1, so +1. Chlorine, -1. Oxygen's usually a -2, except in peroxides like H₂O₂, where it is a -1. So most of the time, based on its family, it's going to have a -1. Hydrogen, in the other case, will have a +1 when bonded to nonmetals, and actually a -1 when bonded to metals. So depending what they're bonded to, we can see there can be some slight alterations to what oxidation number these elements carry. Fluorine always, though, has a -1 in compounds. The sum of oxidation numbers in a neutral compound equals 0, and in polyatomic ions, it equals the ion's charge. So we can see just one quick example down here with a -2. We've got a +6, got a -2. Well, we've got 2 of those. That's going to be 12 in total, and a -14 here. And as a result, the total polyatomic ion charge is a -2, just as one example there. Oxidation states as it relates to the periodic table. Again, hydrogen +1 times 2 would essentially be 2 if there's 2 of them bound to something. Oxygen typically has a -2, as does most of those in its family. And here we see a total of 0 because this is if we're looking at water. So again, we got 1 for our hydrogen, which is located right up here, but there are 2 of them, so it essentially means a total of +2. Oxygen, there's 1 of them in H₂O, -2, therefore your total would be neutral or 0. And this also is a reminder in that periodic table, knowing your families can really help you determine many, many factors. This is just another one, oxidation states. Now, why are they actually useful? Well, they're used to determine if redox reactions occur. They also can be used to balance redox equations in the proper manner, and they're used to understand electron movement between atoms. So when we're seeing this transfer of electrons, when something gets reduced, we're losing electrons. When it gains electrons, it becomes oxidized. These are different ways we can go about tracking this, and using oxidation numbers is a useful tool.